go. All right, so how was the homework assignment? It was okay, okay. Now this is it's not easy to debug, so it really works if you test your program like, okay, I think I got this part done, test it, I think I got this part done, test it, and so on. So do you want me to go over the homework assignment or not? Does anyone, okay, nobody care. Should we go over the homework assignment? I think we should go over the homework assignment, okay? So let's go take a look. And I'm going to download the same file, okay, which is not a whole lot. It does contain the code, so we can use it as a basis. So I'm going to download this file. I'm using Chrome, today, just because I need Chrome for something else, which is kind of cool. I'll show you guys the new toy. I have to change my distribution a little bit so that Chrome is going to be installed. This is not going to stick, so I have to change my live distribution over the weekend to make this work permanently. Okay. So we are taking a look at the source code of the C code. So are there any questions about the C code itself? No questions about the C code? Okay. So if there are no questions about the C code, then we're going to go ahead and convert the C code into assembly code. So I will do the usual thing, which is copying the C file into the TTP ASM, and then we'll go ahead and work on this one. And we'll change all the beginning of each line with // and then the space. So this way I comment out every single line with a single swoop. All right. So we'll do LDI D0 and the JMPI instruction to main, just so that main can be located somewhere else now. So I can now put main over here. And I did not give you a main to test your code, which means you have to write your main to test your code. But you know how to do that already because of the previous homework assignment. So you know what to do to set up the caller. So we'll worry about main a little bit later, and then we'll focus on this one at this point. So we have divide as the entry point because you have to use the same name as the original subroutine. It has got 3 parameters. So now the question is, where are my parameters? So you can, so I'm going to choose to kind of do it like this. On one single line, I want to be able to show what is on the stack at this point and what register D and possibly what register C are pointing to. Okay, so we'll see whether this works or not. So we'll start with the last item. Okay, so we have the divisor, and then we have the dividend, and then we have P remainder. And then at this point, the stack pointer is pointing to the return address. So I'm going to use square brackets to represent what the stack point is pointing to. So this is kind of giving you a view of what is on the stack. Okay, the lowest address is the rightmost item. Okay, I could write it in the opposite way too. Which way do you want? Is this going to work? The left-hand side is the highest address, and then the right-hand side is the lowest address, or do you like to write it the other way around?
This works.
This works? Okay, cool. Okay, so knowing that, we need a place for the quotient, but I don't need quotient to be an actual local variable. So what we'll do is we'll say, okay, we'll keep the same code, or as much as possible, as the previous program, using successive division. Okay, successive subtraction, and then use that to perform division. So what we'll do here is, I'm just going to write the comment here. I want things to be in specific registers. It doesn't really matter which one is which one because I can always switch the order later on. So I'm just going to say A, register A is I want it to be the dividend. I want register B to be the divisor, and I want register C is the quotient. Okay, which register you want to take on each row doesn't really matter. Okay, it really is just a matter of how do we lower all of this stuff. Okay, so the first thing we need to do is a CPR. In other words, we don't know exactly where the parameter is, except we only know what is the relative distance between where the stack point is pointing to and the things that I need to retrieve from the stack. That's the only thing I know is the distance. So in order to do any type of calculation, I do not want to do any calculation with D. Okay, so I want to copy D to C in order to do the calculations. So using this technique here, I'm just going to copy the rest of this line over here. So now we have C and D pointing to exactly the same thing. And I'm going to use round parentheses to indicate what C is pointing to, which kind of makes sense because the open parenthesis looks like C. It's just coincidental, of course. So we'll go ahead and try out this notation. And then the next thing we do is, okay, we need to load it up with different things. So the first one is increment C. And after this increment C, okay, let's see what's going to happen. So after we increment C, then C is going to be pointing to P remainder. Not quite what I need at this point. We do another increment C. Okay, in fact, I'll just copy and paste here. So now we have C pointing to dividend, not P remainder anymore. That's one of the things that I want, and I want to put this into register A. So we use an LD instruction, like so, so that we have A being exactly the same as dividend. It is register A is not the address of dividend, it is the value of dividend. Okay? At this point, C is the address of dividend, but A is the actual value of dividend. Is that okay? All right. But we're not done yet because we also want to increment D one more time. Okay, in fact, I'm going to copy and paste here. So that this time, C is now the address of the divisor, which I also want to put into another register, which is register B in this case. So we have LDBC, like so. So the B is our divisor. Okay. All right. One more thing to do. I want register C to be my quotient. So now we can just say LDIC 0. So the C is now my quotient. I got all the registers initialized. Is that okay? So I put all the important stuff into a specific register, and we are just kind of lucky this time that we have enough registers, so we don't have to keep going back and forth between memory and registers. That will be kind of cumbersome, but sometimes we have to do that. So with any type of loop, I start with while begin, and at the end of the loop, I end with while end. And before while end, I always put in JMPI to while begin. In other words, I start with the structure of the control structure, and then I go back and fill in the content. Okay, because if I do it this way, I won't forget to put a beginning, an end, and also an unconditional branch back to the beginning. If I stay in the loop as long as dividend is greater than or equal to divisor, that means I need to do a compare. And in this case, A is dividend, B is divisor. But I'm going to get out when A is less than B, when dividend is less than divisor. And because these are unsigned integers, so I use JCI instead of JLI. JLI is what you use when we're dealing with signed values. These are unsigned, so we use JCI to while end, like so. Okay, so now we have to implement the body of the loop. We have done this before, so this is not new stuff. So we just subtract B from A, and then we increment C, because register A is dividend, register B is divisor, and register C is quotient. So it just so happens that we have enough registers so that we don't have to put things back into memory and put it back into registers all the time. Yep.
When you say there's a 0 in B and A, would the carry flag still be?
If A and B are both 0, then the carry flag would not be set because 0 is not less than 0. Okay. All right. That's a good question. All right. So now we are done. We're at the end of the while loop here. And we need to find out whether P remainder is 0 or not. If it is not 0, we need to dereference. It sounds like we're going to have to use at least one or two of the registers for something else, right? Now, divisor, I don't really care. Okay, the divisor, in register B, I can use register B readily, but I cannot just use one single register. Yeah, I cannot, because I have to compare to 0. That 0 has to go somewhere. Okay, so I need at least 2 available registers, which also means I have to give up one of the 2 registers that are containing useful information. Register A has my remainder at this point. Register C has my quotient at this point. Both can potentially be useful. I don't want to lose those registers. Okay, register B is fine. I mean, it's just the divisor, and I have no use of the divisor at this point. So you have several ways to fix this problem. You can put it back into the parameters. Okay, that's fine. You can also use a different technique. So I'm going to use this technique here. So at this point, we need 2 free registers, at least 2. Yeah, I'm going to say at least 2 free registers. So what I'm going to do is I'm going to push all the useful values on stack. And to do that is basically just do a decrement D, okay, reserve space on stack. And the next instruction, which is an ST instruction, this is what we are going to use to push the item on the stack. So we're going to store to what D is pointing to, whatever register we want to save. And it makes more sense to save A first, so that it will be the last item to retrieve. Okay, A is my dividend. So I'm pushing remainder. Actually, I take it back. The quotient is what I want to push first. Pushing the quotient on stack. And then we decrement D again. Okay, reserve more space. And I'll go back and fill in the picture a little bit later on. And then we do a ST, D, and then this time A. So we're pushing the remainder on stack, like so. Okay? But we also have to remember to update the pictures, because we have these pictures, they are incorrect at this point. So we'll do a, let's see. Okay. So once we decrement D, of course, divisor is no longer pointed to by C because we changed that already. So after the decrement D, D is no longer pointing to the return address. Instead, it is pointing to some location on stack that has no particular value at that point. But after we push the quotient on stack, we reserve the space first. Then we go back and say, oh, okay, this is where we're going to put our quotient. Okay, and then we do exactly the same thing over here. We first reserve the space, which means now the stack pointer is no longer pointing to the saved quotient. It is just pointing to some location that is not initialized on stack. And then we go back and say, okay, we will put the remainder at that spot. So I guess I can get rid of some. Yeah, I can get rid of this stuff here. There we go. There we go. I like VI. There we go. Okay. So is that okay about the picture of the stack, after the last STD instruction? Is we have all of these items on stack. At the highest address would be the third parameter, which is divisor. And then the stack pointer itself is pointing to the remainder, which we push on the stack, because I want to free up the registers to do something else with the registers. Okay. So at that point, now we can actually try to get this done. Okay. So we are going to do a CPR CD again. Okay. And when we do that, that means C and D are pointing to exactly the same place, which is here. Okay. That's not exactly what we want. That's okay. What we need is to get to remainder. So what you need to do now is to say, okay, I know C is now pointing to the remainder, which is not what I want. I want P remainder, the pointer to the place where I'm going to store the remainder. So you have to say, this is C plus 0, plus 1, plus 2, plus 3, this is plus 4. Okay?
The return address is one thing. The return address is one.
Oh, the return address is 1, right, correct. Okay. Probably would be a good idea to, okay, just hold on a second, let me do this. So it doesn't have a space in between, so we don't count it twice. Okay, cool. So we have remainder is 0, quotient is 1, return address is 2, and P remainder is, okay, it's plus 3 basically. Okay. If we don't want to use up the other registers, we can just say increment, increment, increment. There we go. So by the after the last increment, we would have register C pointing to P remainder. Is that okay? I'm not backfilling the ones in between because it's really just watching the parentheses go one to the left for each line. Is that okay? So this may be something that you can also use on your own when you're reading code in assembly or when you're trying to write code in assembly, is keep a picture of what is on the stack as you write your code. Okay. Is it tedious? Absolutely. That's why people pay you to get this kind of job done. Okay, so now that we know that C is pointing to P remainder, I don't want the address of P remainder. I need P remainder itself and then compare that to 0. So I'm going to use a load instruction here. Okay, since I got all the registers available now, I'm just going to put it into A. So A is P remainder, and I need to compare that to 0. So I'm going to do LDI B with 0. So the B is just 0. So now I can actually do the compare. So compare A to B. And the original C code says, if P remainder is non-zero, then we got something to do. If it is 0, we don't have anything to do. Okay, so JCI works out just fine. JCI is not highlighted either because I forgot to put that instruction into that instruction set thing. Okay, I'm just really bugged by that, so I'm gonna fix that. There we go. Okay, how come JCI is not in here? Because I forgot to put it there. It's simple. Okay, JCI. So we got JCLOSZ. Okay, that's just one of the ones that I forgot. There we go. See? Immediately highlighted. Okay, so we use a JCI to go around the entire conditional statement. So I'm going to jump to end if, which is going to be a label defined here, which marks the end of the conditional statement. And if we get here, that means P remainder itself is non-zero. So now we got an interesting scenario because we need to retrieve the remainder. Because in the original C code, the dividend stores the remainder at this point of the program. But in assembly, we have the stack pointer pointing to remainder right now at this point, which works out really nice. Okay, because what we can do now is we can say we don't want to mess around with register A because register A has P remainder, which we need in order to store the value. But we can play around with register B. So we can do LD B with D, okay? So that B is now the computed remainder. Okay, so let's take a little pause here, make sure everybody understands why register B ends up being the remainder after this instruction. Is that okay so far? Okay. And that's partially why I push remainder last, because whatever item you push last is what the stack pointer points to, which is very handy in this case. Okay, so next instruction is to store to whatever A points to, whatever B has. So this way, we actually finish P dereference P remainder equals to remainder, which is what we want. Is that okay? All right. Okay, so after the conditional statement, we got something to clean up, because regardless of whether we have to store the remainder or not, it is now useless. Okay, because if I skip around the conditional statement, it means, hey, we don't have to store the remainder. The remainder can be popped off the stack. If we get into the conditional statement, it means it's already done. Okay, so either case, I don't need remainder on stack anymore. So that means I need to do an increment D to deallocate remainder from stack. So what that's going to do is it will change the way the stack looks like. I'm going to copy that to here, but use a new line for that, just so that it doesn't look as confusing. So this is now gone completely. And the stack pointer will now be pointing to the quotient that I saved earlier on stack. Is that part okay? So the remainder technically is not on stack anymore, okay? Now this toy processor has no interrupt capability, and that's why, you know, it is actually quote unquote still there, but you cannot count on it in general, okay? So with any type of actual real processor that can handle interrupts, anything that is below what the stack pointer points to can be overwritten without your code realizing it. So do not assume anything below where the stack pointer points to remain intact from your perspective. Okay, all right. So the last thing that I need to do is to return the quotient. Now, when we look at return or the return statement in C, in assembly language, we have to break it up into two parts. One is to specify the return value, which is quotient in this case. The second one is to actually perform the return operation so that we continue execution in the caller. So in C, it is one single statement. It gets both parts done with a single return statement. But in assembly, they are separate concepts. Okay, so we have to remember doing one doesn't necessarily getting the other one done. Okay. So we'll specify the return value first. But the stack pointer is pointing to it. So we'll have to do this, okay, LDA from D. So the A is now the quotient, okay? And at this point, we don't need that anymore, so we increment D. So we deallocate the quotient from stack. So that at this point, the stack now looks like this. And I don't really care what C is pointing to, so we'll just kind of ignore that part. Okay, so C, where C points to, we don't really care. Okay, is that okay? Hey, this is nice, because now, you know, the stack pointer is pointing back to the return address, which is exactly what I need. All right, cool. So we do LDB or C, either way font is okay. So the B is now the return address. And then increment D, don't do the jump right now, okay? You've got to remember to deallocate it first. So we deallocate the return address from stack. It is the responsibility of the callee or the subroutine to deallocate the return address. So now, the stack pointer is now pointing to the first parameter of the call, and we are ready to go back. So we just say JMPB, go back to the caller. So from the caller's perspective, by the time we get back to the caller, the stack pointer is now pointing to P remainder, and it has 3 items on stack that needs to be popped. Because those 3 items, these 3 parameters, are no longer of any use from the caller's perspective. So are there any questions about the subroutine itself? Yep.
Did we really need to push the quotient onto the stack since we're taking it back off the stack in the same subroutine? Couldn't we just have had it in A in the first place?
It depends on whether we need all the registers in order to check whether P remainder is 0 and then use it as a pointer.
Okay.
It looks like we did not need that. Like, you know, register C is never touched here, so we don't actually need to push it.
Okay.
But if you don't if you are not sure, then it's always okay to push it and pop it. It's just consuming extra cycles. But the technique is the important part. Is we're pushing things on the stack so that we say, okay, these values are useful. I need it later on, but right now I need the registers to do something else. So you push it on stack, then you have all the registers available again. You do something. When you're done, you pop those items back to whatever register you needed, and then you're all done. Yep.
Is this the case with some processors running out of registers before they run out of space on stack?
Yes. So all registers will have that problem. Some RISC processors have 32 registers, but if you have a complex, subroutine, you will run out, of registers. And when you do run out of registers, then you have to use techniques either like this, or you have to, or it will save the value of the registers back into the variables represented in C. So most C compilers will try to optimize the code by keeping as much stuff in registers as possible. But since you only have a limited number of registers, you can only keep so much in registers. So at some point, even with processors with a lot of registers, they will run out of registers, and then you have to use tricks either like this, or put everything back, or put certain things back into the registers. Yep, go ahead.
For this sub loop, the subtraction loop, how would we get out if it's like evenly divided, 4 divided by 2?
If it's 4 divided by 2, then it will go through 2 iterations. By the end of the second iteration, dividend will be 0, and then the divisor will still be 2, right? So 0 is less than 2. Time to get out. Okay, so how do we test this code? Well, the proper question is, how am I going to test this code to make sure that you are implementing everything correctly in this case? So what I'm going to do is I'm going to write the actual C code first, and then I will show you how it is going to test your code. So in my code, I'm going to have uint 8 underscore t x y. Okay, so x is 1, y is the other one, and the way I'm going to test your code is I'm going to implement something like this. I'm going to say x equals 2, divide, and with this class I will choose something different from the other class. So I will say divide, I don't know, 255. Let's see, in this class it is p remainder first. Okay, fine. So we'll put the address of y here, 255 divided by, I don't know, 18, okay? That becomes, and then we'll put a 0 here. That becomes the dividend, and then we'll put a divisor, let's say, 5 here. So I'm going to write the code to implement exactly that line of code. And then, technically speaking, there's a return 0 at the end, which is our alt instruction. So that's the easy one. All right, so how do we do this? I want x and y both being local variables. Okay. So how do we do this? It's a nested call, which means it resembles your previous homework assignment. Okay, you have to figure out, okay, how do we push the items, and which call do we perform first? So what do you think? Well, first thing first, we have to allocate storage for x and y. Okay, so we say decrement d, allocate x, decrement d, allocate y. Now, whether you allocate for x first or y first, it really does not matter, as long as you use those locations consistently. So I still want to draw a picture of what is on stack right now. And we have the leftmost part has the highest memory address. So that will be x, and then y is what the stack point is pointing to at this point. Is that okay? Because I want to kind of keep an eye on what the stack looks like at any particular time, because the stack is what we use for many things. Passing parameters, keeping track of the registers, like saving registers and resuming the registers. The return address is on the stack too, so we want to keep an eye on what is on stack at any particular time. Okay, so now we need to come up with the code to do this. First thing I'm going to do is this. Okay, so I'm going to load A with 5 and decrement D, and then we do std5. I mean A. Okay, so after this, the stack is going to look like, okay, oops, just the constant of 5, which is the last parameter of the outer divide call. I'm putting it on the stack right now because I don't want to have to deal with it later. I mean, this would be a good time to do it. And then I need to set up for the inner call. So to set up for the inner call, okay, let me also make it clear that the stack point is pointing to 5 at this point, constant 5, basically. So now we need to set up for the inner call, okay? Same kind of thing. You know, we got 18, decrement D, std_a. Okay, so after this, we got 18 on stack, and the stack pointer is pointing to the 18. Okay, and then we push the 255. Okay, LDA 255, decrement D, std_a. So now the stack pointer is pointing to 255, which is basically 1111 as a byte. And then we need to pass the address of Y. Okay, where's the address of Y? How do I get back to the address of Y? I can use D for the computation. Looks like, you know, if I increment D once, twice, 3 times, I will get the address of Y. But remember, I don't want to mess around with the value of the register, I mean of the stack pointer. Because the moment I move the stack pointer to here, this 255 is no longer guaranteed to be there. So I want to do all the computation using another register, which I just, you know, kind of pick register C for that purpose. So we do a CPR, okay, CD, so that if you look at what is happening on the stack at this point, nothing is really happening to the values. It's just that, oh, we got one more register pointing to the byte that contains 255. But now we can increment it 3 times. 1, 2, 3. Okay, increment C, increment C, increment C. So by the end of the last one, C would now be pointing to Y. Is that okay? Okay, all right, cool. This is what I call really, really self-documenting code. It's actually showing you what is on the stack at any particular time. Okay, so, well, seems like that's exactly what I want, right? Because I need to pass the address of Y as the first parameter to the inner call of divide. Okay, so we will do LDI. Oh, we don't need LDI, it's already in register C. So we decrement D, and then we do std with the value of C, and we'll show what is going on here. So now we have the address of Y being stored here, and the stack pointer is now pointing to just that. Do we have any questions at this point? Is this still doing okay? All right. All right, so we got all the parameters set up for the inner call. It's time to set up the return address. So we do LDI, and I can just reuse register C, it has no value at this point. So we just use this main return address 1 because we'll need another one later on. So this is just the first return address. Decrement D, std C in this case. So we push the return address. Just to be consistent, we are going to document this. So we have main return address 1 on stack at this point, and the stack pointer is pointing here.
And C no longer points to it.
Correct. C is already overwritten. That is correct. There we go. And if you forget to do the unconditional branch, nothing is going to happen, which I forgot. When I talked about the solution for the Monday, Wednesday class, I was actually writing the code along you know, when I was doing the screen recording, and it didn't work. You go like, why is it not working? It just keep jumping to some random locations. As it turns out, I forgot to, actually what I forgot was not to jump. I forgot to save, I forgot to put the return address on stack. So it was using the first parameter as the return address. Obviously, that's not the right location to jump to. So it kept going back to that place, and we're like, why is it going back to that place? So I used the same technique that I talked about in class, turning on the trace, tracking down PC, the stack pointer, and the last few locations on stack. And it didn't take me too long to find out what is going on, because I can look through the code and go like, it's not supposed to go back there. The subroutine was called okay, but it was going back to the wrong place. Okay, so this is the first call. So by the time we get back here, okay, what is on the stack? By the time we get back here, the stack doesn't have this anymore, because it is the call leads, the subroutine's responsibility to get rid of the return address. So this is what you need to kind of remember is, oh, okay, so by the time we get back here, we only got 3 items to clean up on stack. Okay, so we'll do the increment D, and we'll do it 2 more times. So that way, when we are done with all of these, the stack pointer will now point back to this 5. Everything else is now gone. Is that okay? We're now setting up for the outer call of divide, and it is a good idea to keep an eye on what we are actually trying to do. So I'm splitting the screen so that we can keep an eye on the one line of C code that we are trying to do, which is the divide. So at this point, we got the 5 push on stack. We have the return value of this divide in register A, but it is not on stack yet. So it is time to put it on stack. So that means we have to decrement D again, and then STDA. So this way, we have the return value of divide on stack. And the stack pointer, obviously, whoops, is now pointing here. So we got 2 more things to push on stack before the next call. Okay, we have to push this 0, which is the null pointer. It's a 0 address. So we have to do a LDI, just pick one register. Register A is fine. Decrement D, STDA. So when we're done with this, we have all 3 parameters pushed on stack for the outer call of divide. Okay, and we need to do the return address. So this is main return address 2, decrement D, STDA. So now the stack would look like this. Okay, I forgot to put a bracket around the 0. Okay, so now we have main return address 2 on stack pointed to by the stack pointer. So it's time to actually make the call. It's time to continue execution in the subroutine, which is JMPI into divide. And then we define the label, main return address 2. So by the time we get back here, the return address is going to be popped because the subroutine is doing that. And the stack pointer is now pointing back to the first parameter of the subroutine. I got some stuff to clean up on stack. So we increment D 3 times so that we clean up the 3 parameters. So 0, the return value of divide, and the 5 would now be gone. So the stack pointer, once again, would be pointing at local variable y. But that's not what we want. We want to store into x. Okay. So we'll go ahead and do a CPR CD. Okay. I mean, this part is really kind of obvious, but I'm gonna use the same notation. Increment D, and increment C, excuse me, so that C is now pointing to X and not Y, like so. And the return value is in, huh? Oh, okay. Yeah, I made that mistake also, in my other program, and so it ended up storing the wrong thing into the wrong location. Go like, no, it's supposed to store this into X. How can we store it into Y? So that was the mistake. So, but when I track it down using the trace technique that we talked about, that was actually making it possible to look through the trace and go like, oh, okay. why am I storing to the wrong place? Then I can look at the stack pointer value, go like, no, you're not supposed to be there. Okay, so we can now do st instruction to what C is pointing to, because C is now pointing to the local variable x, and A still contains the return value from the outer call of divide. So here we're all done. Okay, this is the entire program, almost. Because at the very end, I'm going to deallocate x and y. So this is deallocate y. Because these two are local variables, so it is the responsibility of the subroutine, which main is, to deallocate these two. So when it's all done, the stack pointer is now pointing to some place other than the stack itself, because it's back to location 0. So, any questions about this code? Are you guys all buying this just because I said it would work?
Yeah.
Well, we don't know whether it's going to work or not. Okay, so we're going to test it. We're going to try it out. Okay. Okay. So we're going to do Control A, Control C, and then this time we're going to use Chrome. Woohoo. Paste, and then we have to make sure that it finished the assembling, making sure that there's no problem. Okay, so that's all good. Looks good to me. So download as CSV, and we'll call this divide in the temp folder. All done. Now it's time to start up the start logic sim. Just look at history and find out which command to repeat. 1973. Okay. There we go. Control R just to make sure everything is reset. Right click, load image, and we want it to be divide.csv. There we go, we got the program. And before we actually start the program, we'll go ahead and log a few items. So we'll log the program counter, we'll log register D at least, which is our stack pointer. Making sure it's in base 16. And then we'll also store the last few locations in RAM. And to understand how much location we need to save or we need to kind of store, we are going to take a look at the source code, because we have a full analysis of how we make use of the stack. So we're going to go back to that slide here. Okay. All right. So from the perspective of the subroutine, okay, the most space we're going to use up would be this part here. So we have 1, 2, 3, 4, 5, 6. The subroutine itself is going to use up 6 bytes, but that's including all the parameters. And then from main's perspective, okay, so this is main's perspective. The most space it's going to consume would be this much. Okay, so 6 on the other one. This one is 1, 2, 3, 4, 5, 6, 7. But of the 7, 4 are overlapped. So 7 plus 6 is 13. 13 minus 4 is 9. So we will need to log at least 9 locations in RAM, because those are the stacks locations that will be used. Okay, so we go to memory, go to RAM, and we'll just pick out the last 9 locations. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. and we'll make it 10, because location 246 really should not be touched, okay? But we want to make sure. So we add all of these and change all of these to base 16, just so that it's easier to read. I do not know of a way other than changing the source code to change the default radix of the log. And then we'll go to File. We'll select a file here to do all the logging. We'll call this divide.tsv. The extension is important in this case because I want to be able to import it into a spreadsheet in Google Documents. And TSV stands for Tab Separated Value, which is what LogicSim is outputting. So we can click Save. Okay, so I think we're good to go. So we go back to the simulator, click type Control-K to start the clocking, and it does come to an end. Type Control-K again to stop. So we can go for a very quick, review of the content in RAM to see whether it works or not. So we will go take a look at the content, and we can see 2 is here, 3 is here. So we need to go back to the code and figure out what is the expected answer. Okay, so the expected answer is y should have the remainder of 255 divided by 18. Okay, since I set up the fancy schmancy document camera, I got to use it at least once in class, right? So we're going to use it for that stupid division. Okay, so okay, that button is at the place where it's easy to click. Okay, so we got 255 divided by 18. There we go. We got 7, right? And then we have 5, 4. 4 is right. Yep, 4 is 72. So we got a remainder of 3. Okay. That works out okay, I think. Do you guys like this better compared to the document camera? Either way, it's recorded. Okay. All right. So getting back to this part here, so that means this number is the quotient, which is 14. 14 divided by 5 has a quotient of 2. So x should end up with a value of 2, and y should end up with a value of 3. So now we go back to the RAM content and say, this is x, x has a value of 2, we're good. This is y, y has a value of 3, that's good as well. So from the output perspective, the program is doing what it's supposed to. We also want to make sure it's not modifying more locations than it needs to. So we look at, this is the last location. As far as I know, this is the last location that it modified, which means we're only using 9 locations instead of 10. So my original anticipation of, okay, we're going to use 9 locations on stack is also correct. But all of those things are important, okay? Because when you're thinking about what this program should do, you should also be thinking about how is it using the stack? How many locations is it going to use on the stack? What's going to appear on the stack, at any particular time when you execute a program. So all of those things are actually really, really relevant to this class. This is basically studying, is to go through this program, do the analysis, figure out what the program is supposed to do, what items should be on stack, run the program. Okay. Now, if it doesn't work, it's even better. Okay, because when it's not working, you're actually learning even more. Because now you say, okay, the program is not working. How do I figure out it is not working? Then you really have to understand the material. So are there any questions about this program? No questions? All right. Does anyone want this program to be uploaded?
Sure.
Okay. Okay. Just checking. Okay. I can see you guys still have a pulse. Okay. So we'll go ahead and do that first before I forget, because I tend to forget things. So we'll go to this part, save, and close. Okay. Okay, so how many things should I zip up here? Okay. I'll put div sub into it, just for the sake of completeness. Okay. I think that should be it. Do you guys want the log? I'll put it here too. Okay. And we need to name file as zip. And then go back to, where is it? Close that. There we go. So we need to go back to, go back to modules. There we go. And just add a file. New file, choose. Pick up stuff from the temp folder. Open. Okay, so now you got the assembly file corresponding to the C source code and also a trace when the program executes. Now the trace is something that you might want to at least take a quick glance at. In fact, I'm going to do that just to show you what it looks like. So you just opened up a Google Sheet. That's one of the easiest way to do it, is to put it into a spreadsheet. And then you go to File, Import, and then you say Upload. And the file that we want to upload is the TSV, or the tab separated value. So click Open. And it will ask you, do you want to replace the spreadsheet? Yes. Separator is for sure a tab, so don't even let it detect automatically. Click Import. And now we have the entire thing. So you might want to do something like changing this one to just stack pointer, which is the register D. And then these are the RAM locations, 255, 254, and so on. So if you know this is going to be local variable X, just change the label to X. This is local variable Y, change it to Y, and so on. Okay. The reason why it looks kind of funky is because when the numbers can be interpreted as decimal numbers, it would just say, oh, this is a number. But everything is actually in hexadecimal. It's just incorrectly interpreting those things as decimal values. Anything that starts with a non-digit or cannot be interpreted as a number, it would just say, oh, it's a string. And that's why the alignment is different. But it still gives you a pretty good idea of what goes on when this program executes. It's a little bit long. Okay. So when you look at the actual length of this trace, it's a little bit long, mostly because of the division. You can see this is basically going through the loop, like that. You can also correspond back to the assembler. Okay, if you go to the assembler, there's a tab called Source Debug, and Source Debug tells you which line is corresponding to which address. So when you go to the other tab, when you look at the trace, and it says, okay, it looks like we're going through C, D, E, F, C, D, E, F a few times. Sounds like location C, D, E, F are in the loop. So you can go back to this code, go back to the assembler, and go to C, D, E, F. Okay, and you can see that C is the beginning of the loop, and D is kind of the end of the loop. C, D, E, F. Okay, so there you go. F is the subtract. And then we have the increment instruction. So that's actually a part of the loop. The loop is not just that. The loop is actually C, D, E, F, all the way up to 1, 2 in hexadecimal. That's basically the loop inside the division algorithm. So the trace is actually really useful when you're trying to debug a program. And the best part about this kind of trace is if you set it up correctly the first time, you don't have to rerun your program because everything is in the trace already. It is just a matter of spending the time to look through the code and go like, okay, is this correct? Is this correct? Is this correct? Oh, okay, this one is going to the wrong place. So most of those problems have to do with returns. If you mess up the stack pointer, it is the return that will mess up and will go back to the wrong place. So those are the things that you have to look out for, is when you return, am I returning to the right place? Such as in this case, the return is all the way to the end, which is down here. Okay, this is my return, which is at location 28. So you have to pay particular attention to, when the PC is 29, what is the next location? So if I go back to the trace, I look at this stuff here, and I go like, okay, let's find out when the PC is at 29. So you just kind of scan through it, or you can use a search. So we go bloop, 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 bloop. Okay. All right, so here's 29, and it goes back to location 43. Then you go back to your source code and figure out, okay, is location 43 a right place to return to? Because those are the most typical issues that you will have when you are writing code in assembly. Is that when you return, it's going to the wrong place. Okay. So are there any questions about the process of writing this code and also the process of debugging this code? Questions? Okay. If there are no questions about this, then the next question that I have for you is, okay, so this one has all the comments. I'm gonna copy it again. Okay, so I have just created I'm creating a stripped version, which is basically getting rid of all the comments. So I'm gonna say anything that starts with / will be replaced by nothing. There we go. I just got rid of all the comments. So now the question is, can you look at this program and reverse it back to the C code? What does this program do? We know there are two subroutines. We know there's divide and there's main. But what is it doing? Can you reverse it? Okay. There's a quick way to remove empty lines in VI, but I cannot remember how it is done. Okay. So I'm gonna try here. Locate anything that has an empty line and delete those. Okay, it only does it for one. Look for it. Vim, remove empty lines. There we go. Oh, okay. So it's a G. Okay, there we go. G. There we go. Almost. Some of these lines have tabs left over, but close enough. Okay, so, but the idea is this, okay? I give you the assembly code with no comments whatsoever. Now, in the exam, I'm not going to give you something this complex to analyze. But for something simpler, how do you, it's the approach, okay? How do you get started? And how do you figure out, okay, this is a parameter, we are accessing this parameter, blah, 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 and so on. So what do you think? How would you get started if I say, give me the C code corresponding to divide. We know divide is a subroutine. It's using the convention that we have been talking about. The parameters are pushed on stack. The caller, is responsible to push the return address. It is where the stack pointer points to. Register D is the stack pointer. If I give you all those conventions, which we have been using, all the way up to this point, how do you reverse engineer this code and say, oh, we can say that this is a parameter, this is a local variable, this is what we're doing, there's a loop here, this is the exit condition, da 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 da. Yep, go ahead.
You can say that all the increments and loads, you can kind of guess at their parameters.
With all the LD and ST instructions, you're dealing with memory. So unless you're unless you're using global variables, they're most likely doing something on the stack. Yep. But how can you differentiate something that is a local variable versus a parameter?
The parameters are all above the where key points to when you go into.
Yep.
And the local variables are below.
Yep, exactly. So there are a few things that I can, at least talk about. I have not formulated this kind of discussion before, but I suppose we can always do that. How do I make a new page? I guess plus. There we go. Obvious. Okay, so when you set up the stack, okay, the way I draw the stack or any type of memory is always like this. High memory address. Oops. Switch back to this tool. So high memory address is always at the upper side, and then this is low memory address. The parameters are always pushed by the caller, and that's why the parameters will be at the last few locations. So depending on how many parameters you have, this portion can change in size. After the first parameter, okay, so I'm going to put a specific name here as param1, because the first parameter is pushed last, and therefore it has the lowest address in memory. Below the parameter 1 is the return address. It is also pushed by the caller. Okay, the callee needs this to return, but it is the caller's responsibility to put it on the stack. Anything below this is the callee's or the subroutine's responsibility. So everything to this side, okay, these can be your local variables, and also just temporary use of the stack. And I'll just call it temp use stuff, just like what we did to save the register, so that we can pop the registers to reuse the values. So everything is on that side. The problem is the stack pointer floats with the use of the stack. In other words, when your subroutine gets control, okay, you are guaranteed that D points here at the entry point of the subroutine. But that's the only thing you're guaranteed. Throughout the execution of the subroutine, if you push more stuff on the stack, your D is going to move down. As you pop more stuff, your D is going to go back up. So the subroutine has to track that. Is that okay? Which also means when you are dealing with code like this, okay, if I give you just the assembly code, and you have to basically figure out what is going on, then you have to basically redo the documentation that I did earlier and find out what is on the stack, what am I accessing on stack. Okay, so for each line, you will need to do a documentation. It's like, okay, I know for sure, okay, after this first CPR instruction, C is pointing to the return address because it is the agreement. And then we say increment, and then do an LD. Okay, so the two increments are important. The first increment moves the C, so it points to the first parameter or the first byte after the return address. The second increment makes it pointing to the second byte on top of the return address. Okay, but it is significant because we are loading that into register A. So now we can say that, okay, A is some kind of parameter. We don't know what it is until we figure out how we use it. We just know that it's one of the parameters. We increment C one more time, so we are accessing another parameter. So it's the analysis of how we access items on the stack that will give you an idea of, okay, we are getting to the parameter. Okay, we're getting to the second parameter, we're getting to the third parameter. In the tests, I'm not going to trick you guys and go like, oh, this parameter is a 16-bit integer. Okay, so I can always give you and say, okay, every parameter is 8-bit wide. So when you just count the number of increments, you can kind of tell, okay, which parameter am I accessing? Is that okay? How do you identify? Yep, go ahead.
I was just going to say the LDA comma parentheses C. What does that look like on the stack?
It doesn't do anything to the stack. It retrieves whatever C points to and put it into A. Now that is a question that really needs to be answered when you're studying. Okay, I'm assuming that when you look at all of these instructions, you know exactly what each one is doing. Okay, that is a basic assumption. It's knowledge. Okay, because the test that I give you guys is not about knowledge. It is about the application of knowledge to solve problems. Which means, you have to have the knowledge first in order to use the knowledge to solve problems. So when you have something like this, okay, and you go like, I'm not really 100% sure what this is doing, okay? What do we do to figure it out?
Opcode table.
There are two places, okay? So I talked about this with the other class as well. So there are two places. The first place is you go back to the website and you go to the processor folder. This is the opcode table, which is really useful. Okay, so when you look at the opcode table, it tells you, it looks a little bit cryptic. The first column, or column A, gives you a bit pattern, the basic bit pattern of a particular instruction. Let me zoom in first so you can get a better view of what I'm talking about. Okay, so I think that's pretty good. Do LD, so we locate LD, and LD is here. This is the LD instruction. So this tells you that the opcode of the LD instruction is a template of 0111, which is a 7 in hexadecimal, and then we have 2 bits to specify register X, which corresponds to the first register that we specified, and then we have 2 bits to specify register Y, which is the one that we specify in parentheses. Okay. What is that going to help? How is that going to help me? Well, the first thing is you look at column C. Column C is describing the effect of that instruction, but using C notation. So in this case, we are saying dereference Y and use that value, okay, to store into X. Y is a register, X is a register. So what we're doing is we say, okay, Y, you're a register. Whatever memory location you point to, we retrieve the value of that location, and then we put it back into X. Okay? So I think this is the first step. This is probably the most intuitive way to understand the instructions. But for certain ones of these ones, it may not be that easy to understand. Like JZI, looks kind of cryptic. So what do we do when we encounter something like JZI, which is a little bit cryptic because I describe it as using a ternary operator, okay, which is actually correct. Okay, this is actually the correct way to specify it. But if you have, if you want to look deeper, the other way to look into and find out what an instruction does is to use the simulator. Well, okay, not quite the simulator yet. And I'm going to point out another resource that is available to you. It is in this folder. It's called opcodes.zip. Okay, so if you download this and unzip it, it will give you a folder. What is going to be in the folder is this. Okay, I can show you exactly what it has. This is the content of the folder. I can make clean to get rid of all the unnecessary stuff. This is what you get, a bunch of .c files. And the way to make use of the .c files is to do it like this. Okay, you can use whatever editor you want. Okay, I would definitely use something that can display things, side by side. So was it JZI that I was talking about? JZI. Okay, so we have JZI.c, but you also want to look at ucode.c, because ucode.c contains the actual subroutine called by JZI.c. So I'm displaying these two side by side. On the left-hand side, we have JZI.c. On the right-hand side, we have the other one, which is ucode, microcode.c. So this is basically how we specify each slice in the ROM, in the microcode ROM, okay? But in a way that is easier to parse. The first item, but you do have to do some counting, unfortunately. So you do have to do some counting. Let's say you're not sure what this is, what this one really means. It's the fifth item. 1, 2, 3, 4, 5. the fifth item is address mux. So in this particular instruction, or the first slice of JCI, we specify a 1 for address mux. Okay? We also specify a 1 for PC mux. We specify a 1 for PC enable, which means this one is going to change the program counter. We specify a 1 for microcode pointer select, which typically means it is just incrementing the microcode pointer. And also we specify 2 1s close to the end of this list here. Okay, so when you go and when you move on to this side, you say, what are the last 2 items of this list? These 2 items correspond to these 2 items here. So we are specifying a 1 for RAM load, which means we are reading from RAM. It is also putting a 1 into RAM cell, which is going into the select pin of RAM, which means we are using RAM in this instruction. But how are we using RAM? Who is driving the address bus? Who is interpreting the data bus? Blah 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 blah. You have to look at the actual code in this. Look at how the multiplexers and demultiplexers are set up, which register is enabled, which ones are disabled, and so on and so forth. Then you know exactly what is happening when this instruction executes. And that is what you're supposed to study. Is that okay? No? Okay, which part is no?
Oh, just the fact that we have to study that.
Oh, you don't have to study this. I mean, this is also represented in the actual microcode sizes. I'm just giving you several ways to do it, many different ways to do it. So when you look into the simulator itself, which is right here, so when you execute a instruction in the simulator, it actually goes to the code. It actually goes to the microcode. So if you single step through it, you can actually just freeze the processor in time and go like, okay, what is getting activated? What is enabled? What is disabled? How is this mux configured? How is that demux configured? So you can, if you're more visual, use the simulator. It has exactly the same thing. What the C code is doing, okay, is this is really my tool. Okay, this is my tool to generate the ROM file for the simulator. Instead of doing everything by hand, I do it this way so that I don't have to spend all eternity to go like this opcode specify these 27 bits. The next one specifies these 27 bits. So what the source code is doing, all of these things, is really a quick way for me to crank out all those microcode slices, so that if I make a mistake, it's consistent. I just have to fix one bug, and then it will regenerate everything else. So this is more or less a source code way of looking at things, like how is the add instruction specified? Okay, so we have certain types of fields that are used, just whatever is YY goes here, whatever is in XX goes here, whatever is in XX goes here, and you can also bet on this particular one has ALUEN being a 1. The ALU is enabled in this case. Okay, so that's one way to look at it. If you like to look at things from the code perspective, this is a good way to do it. If you're more visual, then doing it this way is the other way to look at it. Okay, just write a very simple program. Okay, add A, B. Okay, adding register B to register A. As you execute the code, single clock, Control T, and then Control T. When it gets to the actual microcode slice of the add instruction, stop. Okay, look at all the pins that are enabled. What is going into the first input of the ALU? Track it down. What is going to the second input of the ALU? Track it down. Look into the ALU itself. What operation is enabled? Am I adding? Am I subtracting? How is that specified? Track that down. How is the overflow pin calculated? Track it down. Because everything is actually documented. It's all open. That is the reason why I use the toy processor in this class, is because it really is fully self-documenting. So is that okay? I mean, do you guys kind of know what you need to, how to study for this class? I would say for the most part, okay, you know, I did it in many different ways, but I would say for the most part, the opcode table is the most concise way to understand the instructions. Okay, so normally I would just print this out. Okay, if I were taking a test in this class, I would definitely print this out on a piece of paper, or prepare it in a certain way that I can locate the instructions quickly. But I would also go through each and every single instruction and understand what it does. Now, how do I understand what something does? For instance, I look at the JCI instruction and go like, yeah, I think I got it. I think I know what it's doing. Okay, then I look at the actual effect in C. It seems like what it's saying is, if Z is non-zero, which means when the Z flag is true, then I'll look into the ALU to find out what the Z flag is, right? If the Z flag is true, then the program counter is updated by what the program counter is pointing to. Because that's what it's saying. There's a little asterisk here, which is a dereference. If the Z flag is a 0, then the program counter is just going to be incrementing itself, so we're moving on to the next location. So that's the C description of what the instruction does. Then I would go like, okay, I want to test this. I want to see whether this works or not. So what I can do is I can have a single JCI instruction in assembly code to go to one place that is not the next location. Okay? And then in the simulator, okay, so let's just say that we want to test this. The opcode, so I'm going to do this exactly, and to illustrate, how I would study for this class. So I'm going to close this, go back to the command line, rerun it, because every time we trace, it kind of messes up. Okay, so going back to the opcode table. So I'm going to inject this opcode into the RAM directly. Okay, I'm not even going through the assembler. I'm going to say this is 4, 5. 0, 1, 0, 0 is 4. 0, 1, 0, 1 is 5. So it's instructing opcode is 4, 5. So I'm going to here, and I go straight to the RAM and say, I'm going to change this location to exactly 4, 5. But it looks like it will also need the next location. So it's going to need the next location to tell it where to go when the Z flag is a 1. Okay, so we'll specify the next location and say, oh, if the Z flag is a 1, we'll go to location, I don't know, 0C. Okay, just because 0C is here and it's easy to see it. And then we'll say, okay, after the instruction, we'll put a halt instruction. We'll stop the whole thing so that we don't get past that point. So getting back to the opcode table, we look up halt, and the halt instruction has an opcode of 0, 1. So we put a 0, 1 here. If we do not get the branch, we will stop here. If we did perform the branch, we will stop here. In other words, I have just manually constructed a very simple program to test how JZI works. Okay? In order for this program to work and say, I want to test the case when the 0 flag is a 1. Okay, how do we test that? We have to inject a value into the flags register, which is here, so that the Z flag is a 1. But which one is the Z flag? There are two ways to find out. One way to find out is to go to the ALU. Okay, so you go to the ALU, and then you go to the flags out, okay, which is here. And you go like, okay, which one seems like the flags for the 0 flag? It's this one. It's bit 1. Okay, so you want to set bit 1 to a 1 if you want to test whether it's branching or not. There's another one you can also use if you're not a visual person and you want to look into the source code to find out how things work. So this is how you can find out. So you can look into jzi.c. And one of these ones is the PC muxmux. Okay, so PC muxmux is, I think, the 4th one. I could be wrong here, but anyway, the PC muxmux is a 1. So you go back to the diagram, go back to main, and you say, okay, what happens when PC muxmux is 1? PC muxmux goes here. Okay, it's reminding me that it's time. Okay, so PC muxmux goes in here, which also means I'm going to pay attention to bit 1, but that bit 1 comes straight out of the output of the flags register. So either way, it confirms that the 0 flag is bit 1 of the flags register. So to test this program, I'm going to finish this whole test before we move on, before we get out of here. So we have to inject a value of 0, 2 into flags, because 2 means bit 1 is a 1. All the other flags are zeros, but the Z flag is a 1. Is that okay? So this is how I set up the experiment. And then I do a Control T to single clock through the whole thing. So I want to pay attention to the ROM, okay, because I want to track down to location 450. This is the actual slice of microcode that is telling the processor how to run that JZI instruction. So now we go back and then we analyze. We know for sure the program counter is getting updated because the program counter has its own enable being a 1. Okay? So the question is, how is it updated? Well, it's updated through this wire. We know that too. But it's going through a mux. So we have to look at this mux and say, okay, what is the select of this mux? It is PC mux, and it has a value of 1, which means we are selecting this line to update the program counter. But this line itself goes into another mux. But this mux has the select pin being a 1, which means it's coming from here. You track down this wire, and it does go all the way back to the data port of RAM. In other words, we are reading a byte from RAM to update the program counter. Then the next question is, which location are we reading? So in order to know which location we are reading from, you track down the A port, okay, of RAM. The A port of RAM goes back to this mux here. This mux is controlled by the address mux. The address mux has a value of 1, which means we are using this input to drive the address port. This input is going back to the program counter directly. So that means we are using the program counter to specify which location in RAM to read. But what we read from RAM is going back to update the program counter itself, which, going back here, is performing JZI, right? Yep. Which is performing this part of the operation. So then the next thing you want to do is to say, okay, what happens if the 0 flag is a 0? Reset the processor, or just reset the processor, leave the RAM alone. And this time you want to inject 0, 0 into the flags register, and then Control T through this code, and then figure out how the pathways are set up when the 0 flag is a 0. That's kind of how we study for this class, or how I would study for this class. Is that okay? We haven't really gotten into the practice test, which we'll do next Tuesday. So that means the actual exam 2 is going to be 1 week after next Tuesday. So we have about, 7 plus 5, which is 12 days before the second exam. So you might want to start preparing for the material for the second exam. All of this stuff that we talked about is relevant. You need a picture of the processor itself. You might want to have your own copy of the Opcode Table, okay? Index in whatever way you feel is the most efficient way of indexing into the operations. Sample programs, okay? You can print out as many sample programs as you want. What I just uploaded today to Canvas, okay? You can print out the whole thing. Print out the C code, print out the assembly code, document it the way that you want to document, bring it along. So next Tuesday, what we'll do is we're going to go over some practice questions from past exams, so that you have an idea of what kind of question will be asked. All right? But that means it's a good idea to study over the weekend, so that on Tuesday, next Tuesday, when I have the practice questions, you can actually assess for yourself and go like, yep, I got that, I got that, I got that. That I'm not really clear about. I'm going to have to study that a little bit more. Okay? So that's what we will do for the next few days. No outstanding homework assignment at this point, but you might want to kind of pick up, if you want to, I can go to the lab and give you some ungraded assignments just so that you can practice. Okay. All right.